So what we hopefully will cover for today's class, we'll see like the feature matching and then image transformation with some like kind of transformations and then transformation and projective geometry. And if time permit, we'll go like even more with the classification. But before we move forward, I would like to give like some hints for previous class. We mentioned earlier that we can change the size of the sigma or my Laplacian filter. And if I'm doing or try to do the apply the filter to each of this image, I will get like different response. And we also mentioned that the maximum response I will get if this matches the size of that. Okay, but I just would like to give a hint on something like this because the scale of the blob is happening by convolving it with the Laplacian at several scales, as we already mentioned, searching for the maximum response. But the Laplacian response decays as scale increases. So assume that here I have this from -8 to 8. And I'm applying a Laplacian with Gauss with sigma, equal to 1, sigma equal to 2, sigma equal to 4, and so on and so forth until sigma equal to 8 and sigma equal to 16. But I was expecting that when I have sigma equal to 8, I will get the maximum, correct? And this is what we have already shown in the previous slides. There is a trick that you need to take care of, which is basically that I have to multiply the Gaussian derivative by sigma. I have to do this by sigma in case I'm assuming or I'm using a derivative of a Gaussian filter in this case. So if this is the situation with the Laplacian, the second Gaussian derivative, so it must be multiplied by sigma squared. Okay, so how this will change? If I have this is my original unnormalized Laplacian response, when I do the multiplication with the sigma square, luckily I will get the maximum when sigma equal to 8 as expected. And this is what I'm expecting, yes, to get the maximum with sigma equal to 8. The only thing that was missing is just multiplying by that particular factor. So this hint, hopefully it will help you understand a little bit why we got these different responses. So back to SIFT. What we have covered previously that, okay, at the end, I will have a certain particular patch. Inside that patch, I would like to build my descriptor. What is the descriptor? It's just, I would like to create a description about the little local neighborhood of the points. Ultimately, I would like, assuming that I have an image like that, that there is another image which has like different transformation, rotation, translation, whatever the image or the other image is, we would like to say, for instance, that that particular small patch corresponding to that patch, that corresponding patch corresponding to that patch, and so on and so forth. But we would like, or what we have described is how to do that, build that particular descriptor. And this descriptor is shown as we already explained here, that I will take the gradient and then I will take the histogram of that particular gradient and so on and so forth. But that descriptor needs to be distinctive, meaning that that descriptor, for instance, will be distinct from another descriptor for another box. And why is that? Because I would like actually to do the match ultimately at the end. I would like to match some of the boxes here to some of the boxes here. So if it has each one of these distinct descriptor, so I should be able later on to do something like that much easier. Okay, so we create the histogram of the oriented gradient, and we said like we also take into consideration the magnitude of that gradient, and the corresponding magnitude of that gradient will have like more weights and so on and so forth. And by the way, we can also apply a Gaussian weighting. So for instance, if this is like the center of my small patch, I will weight a little bit more points like in the centers of the gradient in centers more than like in the far apart from that particular place. So all of this, something that we mentioned. How to calculate the gradient here is just like what we expect to do when I get the m and the theta. So if this is alpha or theta, for instance, then alpha or tan theta will be this side over this side, as you can see from here. How we calculate this side or this side is not but the difference in x divided by the difference in y. When I get the magnitude, it is the square root of the difference in x squared plus the difference on y squared. Yes? So just like the difference x plus 1, x minus 1, y plus 1, y minus 1. So I'm just taking, this is vertically different in y. And then I'm taking this different in x in order like to calculate that one and so on and so forth. And then if I have a gradient like that, I would like to see what is the gradient. Of course, I'm expecting that m in this case will be equal to 1, the square root of the difference in x's. Since there is like a difference in x in that direction, so I'm expecting that, of course, I will get a value. There is nothing in this, so I'm expecting on the other side will get 0. And then the theta will be arctan of this 0 over 1 will give me 0. So it's something like just horizontal. I'm expecting something horizontal like that. If it is like this, of course, I'm expecting the other way around. The m will be also 1, but the square root of the difference in x, there is nothing. There is 0. The difference in y will have a certain value. And then the theta will be the arctan over this will give me a 90 degrees. So I'm expecting that the gradient will be like that. And this is what we got. Also, if it is like has an inclination angle like this, let's say like 45 degrees, I'm expecting that we'll have a gradient with the value in the x and the value of the y, and at the end the theta will be 45 degrees, which is this is the case, and so on and so forth. Okay, so after that we said that okay, from these particular gradients we will get a concatenation of 128 histograms. Why 128? Because this basically will be divided to a 4x4. And each one of these 4 has 8 orientation. If you go back to this, yes, if you count the orientation for each of these, by the way, as I mentioned, they should be like 4x4. It's not like that, it's just like for simplicity. It is 4x4. Each one of these has like an 8 orientation. Then you can count them. For instance, at the end, you have like 128 of these. After doing the histogram from 0 to 2 pi, you will have like a histogram for each of these quarters. Okay, so now we have the 128 dimensional descriptor, and then, or let me ask you another question. What if any of these gradient magnitude or the magnitudes of the gradients for some instance is very high? Unfortunately, if it is very high, will dominate the other gradients, and it might give us a false orientation. How can we solve something like that? We can solve something like that by just like saying like, okay, now I need to clip at a certain particular threshold, for instance. At the very beginning, I will do a rotation normalization, and then I will clip that at 0.2, for instance. And then after that, I will normalize the descriptor. The whole descriptor, I need to divide by the whole magnitudes. So this is, we understand why we need to do that in order like just to eliminate one, for instance, a higher magnitude value. But why we need to normalize the descriptor? We need to normalize the descriptor because at the end, if you remember, I told you that after we have a descriptor from the left image and we have a descriptor from the right image, we need to do a feature matching, correct? And if I would like to do a correct feature matching, I have always to normalize my magnitudes. So the left will have like the normalized magnitudes, which will be equal to 1, and the right magnitude, normalized magnitude will be equal to 1. So when later on, I will do these features matching as we will describe later today, the results will be a little bit more correct than if it wasn't normalized. So if this is the case, then I have the clipping with a 0.2, then each of these will less than 0.2, and when I am doing the normalization, the sigma of all of these will be equal to 1. Okay, so now we have this image, and by the way, we are taking approximately some locations close to each other here, normalize the region, create the descriptor. We normalize the rotation, all whatever I already did explain, we have already applied here. The question is, how then we'll do the feature matching? So I have a descriptor, then how I can say like, now I can do a feature matching. This is, I have to determine correspondence between descriptors in two images. If this is correspond to this, this is correspond to this, and so on and so forth. We already explained the detection, identify the interest points with the Harris corners and all of this kind of stuff. Then the description with the explanation that we just showed using the SIFT algorithm. Then we would like to do a feature matching. So how we can do a feature matching? Let's say I'm giving you a feature in image 1. How we can find the best match in I2? There are like a couple of ideas that we can actually pursue. Let's say I will define a distance function that I'm comparing these two descriptors. Let's say for that, I will have like a distance function, and as much as that distance is close, so I can say like this is like a good match for that particular point. Or I might do like a correlation, and the highest value will give me like a highest correlation value, means like a highest matching, and I might say that this is matched to the other one. Or maybe I will do something called normalized cross correlation, as we will also cover later on today. At the end, I have to build a certain particular distance function that will measure or compare these two descriptors. Then I will test all the features in I2 and then find the one with the minimum distance, for instance, if I am assuming, or if I calculate it through the sum of the square difference. But if I choose to do that using the normalized correlation, that might be also another option. Just like to review what is the normalized correlation. The normalized correlation that I am doing the usual correlation, but with some like small changes. I have to subtract the mean from each image. Suppose that U is the first image, V is the second image. I have to subtract the mean, as we already described earlier. Subtract the mean, just remove any DC component or any DC offset. But more than that, I have to divide it by this magnitude square. In another sense, I just would like to make the normalization. If I'm doing that, so the score values will range now from 1 to -1. Why? Because when I have the normalized patches, you can think of this as just a vectors, or let's say like unit vectors. And when you do correlate the two unit vectors, it just will give you like either maximum will be 1 or the other way will be -1 if they are totally uncorrelated. And that's why we might, in some cases, think that normalized cross correlation might give us a match or a better match value rather than other particular distance we might choose. Okay, assuming that I have choose the sum of square difference. So now I have the sum of square difference, but unfortunately it is not invariant to intensity change. If I choose the normalized correlation, luckily it is invariant to affine intensity change, as we have already described. So for instance, I have here an F1 box, small image, small patch, I will call that F1. And I would like to find what will be the best match into the other image. And let's say that that best match is in F2. But for some instance, as you can see here, when we found the best match, it might not be like a good match, or it might not be a correct match. The question is, so this will give us, for instance, like a small SSD value. And then I will say, falsely that F2 is the best match for F1. I might say like another F is the best match for F1 and so on and so forth. So which value or which SSD value do we have to say that this is a good match or this is a bad match and so on and so forth? Let's calculate the L distance or the L2 norm distance between F1 and F2 for instance. But unfortunately, this might not be a good way to calculate the stuff. What is better to do is basically to have a ratio distance between the image and the best SSD match coming from my calculation divided by the image minus the best second match of this second particular match on this image. So I will say like, hey, this is my image, this is my best match, this is my second best match, and then I will calculate that ratio. I will calculate the ratio between the distance to the best match divided by the distance to the second best match. Why is that? Because luckily, if this particular ratio is low, that particular will be a good match. But if this one is high, unfortunately, this will give me an ambiguity and this is not correct. So I can like exclude that from my calculation. I said like, hey, no, this is not a good match or this is not a correct match according to this. Because if both of them are very close to each other, for instance, so the value will be low. Yes, so I'm assuming now I have this correct. When I have this both ratio, I am in the right direction. So I will not do the false 2 times. But if this is like very far, so no, now it is not correct. And I'm, for instance, like I have already choose a not correct measured value or a not correct measured, or I didn't find a correct match signal. If we try to do the graphs in order like to choose like a certain particular threshold, the ratio of the distance closest to the next closest with the distribution of the probability function, for instance, I will find that it is going like that, increase, and then decrease, and so on with the good matches. And this is just like with any like not correct matches. If I were to ask you like where will be like a good particular threshold that I would choose in order to take all of the good matches. If you look at these, all of these like a good matches, so I might say like, hey, I can like take the threshold at this particular place, for instance, 0.8. So anything in this domain, I will assume it is correct, or this will be the correct match. I'm just trying to choose a certain particular threshold to my values. Okay, but then next, I have done all of these things. But the problem that I would like to know exactly what is the transformation between one point and the others. Let's say like this point x dash and this point x, and I would like to see what will be the transformation between this point and that particular other point. Because if I will know the transformation between this and that, I would be able to know the transformation between this and this, and between this and this, and between this and this, and so on and so forth. So basically, we need to get what is the function that transferred between x dash and x, or between x and x dash, no matter what is exactly the thing is. So let's say like we have the 2D transformation. Assuming we have like a translation, rotation, aspect, affine, perspective, cylindrical, and so on and so forth. Let's take one by one. Assuming that this is the image, and then after the transformation, it looks like that. So what I did is just like scaling. But how we can implement the scaling? The scaling is not but just multiplying by a scale. So the x dash will be a multiplied by the original value. The y dash will be b multiplied by the original value. Okay. Can we put this in a matrix form? Yes, we can do that. X dash y dash will be a0 and 0b multiplied by xy. If you do the multiplication, ax 0y, so it will be x plus by. And this is equal to x dash and y dash. Okay, so this matrix can be a representation of the scalar. The diagonal has like a certain particular scales, 2 scales, 1 in each direction. The off diagonal is just 0. How would we implement shearing, for instance? Again, shearing is not but just like translation with the scale. So x dash will be the original x plus the scale multiplied by the y direction, because the shear is just like going like in the other direction. And the y will be a translation on the x plus the y direction. Can we put this in a matrix form? Yes, we can. If you do the math, you will find that this matrix represents the shear transformation. 1 in the diagonals, 1s in the diagonals, different scales in the off diagonals with A and B. Here is the rotation. So here I have the point x has been rotated to an x dash, y dash. A point vector x, which has an x and y, is basically rotated to that location, which has like an x dash and y dash with this rotation theta. Again, how we can implement the rotation? As you know, x dash is equal to x cosine theta minus I sine theta. Y dash is equal to x sine theta plus y cosine theta. No, we don't believe you that this is the correct one. Okay, let's see like the proof. So this value x, the x value here is not but r cosine phi, correct? This value here, the y, is not but r sine phi or sine phi. So x equal r cosine phi, y is equal to r sine phi. Correct? How about this one? Let's calculate the x dash. X dash is r cosine this plus this, correct? Because this is the whole theta or the whole angle. So it is r cosine theta plus phi. R cosine theta plus or phi plus theta. How about this? The same things. R sine this plus that. So this is r sine this plus that. Okay. But do you remember trigonometric identity for cosine phi plus theta or sine phi plus theta? If you review that, you will find that cosine is cosine cosine minus sine sine, if you remember. The sine will be sine cosine plus cosine sine. Okay, so now I have the x dash and y dash in this representation, but I can easily substitute r sine phi by y, and then r cosine phi by x. So this is basically will give me y cosine or x or r cosine, whatever, like the substitution that you will get from here, and then plug it, you will get whatever I told you in the previous slide. So now we have already proved that x dash will be equal to x cosine theta, because this is r cosine phi is x cosine theta minus r sine phi, which is r sine phi is the y here, so it is minus y sine theta, and so on and so forth. So now we can represent with this equation the rotation. But again, the same question, can we put this in a matrix form? Because as you will see later on, we are just playing with the linear algebra stuff. And when we play with the linear algebra stuff, we always need to play with the matrix and vectors, and instead of just like the algebraic notation. Can we put this in a matrix form? Yes, we can. If you do the math, you will find that this cosine theta in the diagonal, and then the sine theta with a minus sign here in the off diagonal is representing a rotation from the vector xy to the vector x dash y dash. So now we have seen a lot of this transformation in the matrix form. So at the end, I will have an x dash, and then will be transformed through a certain particular matrix transformation, we'll call it M, which is transform the vector x and y. So we can see like scale. If you remember, scale is just like scaling in the x and y. There is nothing in the off diagonal. Rotate, we already showed. Shear is already here. The flip across the y, by the way, if you do the math, you will find that this is the matrix. If you flip across again, this will be the matrix, or you just have an identity matrix. So at the end, you have different M to do different particular transformation. But then next, we have like to handle the easiest transformation, which is just translation. How can we implement something like that? Okay, so if we would like to implement something like that, let's like this is the center. It will move, as an example, that amount in the x direction, and it will move that amount in the y direction. So now I arrived to this point. X dash is not but x by transformation in the x direction, and y dash is not but y and then transformation in the, yeah, I think this should be y direction. How about matrix representation? Can we allocate that in a matrix representation? Can you think of a way that we can allocate that in a matrix representation? Not possible. We cannot do that. Given this information, unfortunately, we cannot put this in the matrix representation. But how we can solve that? Because at the end, we need to play with the matrix. So we have to allocate this in a matrix representation. And we need to find a way that we can do something like that. How is this way? We will exploit the projective geometry idea. So what we have right now, x and y, which we will call it heterogeneous coordinates. What we will transfer these coordinates to another things called homogeneous coordinates by just adding a 1 here. What does that mean, physically or geometrical point of view? What is the meaning of adding a 1 here? When I'm adding a 1 here, so this is not but I have my 2D point in my 3D point space. In that 3D point space, I have an x, I have an y, but I have z equal to 1. So I have moved that place to another place in the z direction at z equal to 1. So I just moved that. Why is this? You will see this just in a second why we are doing that. We can also multiply by a scale. Let's say like I multiply by the w or by the a or by the whatever the value, ax, ay, and this is a multiplied by 1 will give me a. So instead of just like doing that, I scaled that. The idea is exactly the same. I'm just transferred that 2D in my 3D image domain, and I have pushed that in z equal to 1. If I would like to go from here to here, I will add that 1. If I would like to go from here to here, I just remove that 1. Or just like to be a little bit more precise, if I would like to go from this to this, I will multiply by the scale a and add the 1 multiplied by that scale. If I would like to move to this back to here, I have to go first to this by dividing the scale and then by removing the 1. And this is going from the homogeneous coordinates, or sorry, from the heterogeneous coordinates to the homogeneous coordinates, or vice versa. So now we can do this in matrix representation? Yes, we can. After doing this in the homogeneous domain, we can actually write our matrix M in that particular shape. So now I have x dash, y dash, and then 1. The transferred direction or translated direction. Here is my original direction, and this is my matrix. So x dash has been transferred 1 plus x, yes, which is x, plus 0 multiplied by y is 0, tx multiplied by 1 is transferred in the x direction. If you recall, this is what we had earlier for the transformation, the translation. How about this y dash? Y dash is equal to 0 multiplied by x, so 0, 1 multiplied by 1, so y dash will be equal to 1, plus ty multiplied by 1, so translation in the y direction. So now I can use this as a translation or as a matrix for my translation domain, as this house, as an example, has already moved 2 in the x direction and then 1 in the y direction. That house will move to here using this transformation. So just to review again, from heterogeneous to homogeneous, I'm going to that. If I am going from homogeneous to heterogeneous, I just like, sorry, I have it like that. I am dividing by that factor and then removing the 1. Scale invariance, meaning that if I multiply by a scale, it will not make a lot of invariance. But now we would like also to look at the point a little bit differently. So again, this is my image plane. So this is my image plan, and this image plan has been already allocated at z equal to 1. So as an example, the image plan can be here, the image plan can be here, and also the image plan can be just at the 2D image only at that particular location, for instance. But I just moved that to z equal to 1, and I have done my representation. And this point x in that particular homogeneous coordinates is not but x, y, and my z is equal to 1. As we will describe later on, if I would like, using the projective geometry, to look at this point differently, this point is not but the projection of this point at the 0 location intersecting with that particular image plane, correct? The x point is not but the projection of this P point to the original origin here, intersect at that particular location. So for instance, if I were to ask you what will be the value of this, or what will be the value of this, or what will be the value of this, and so on and so forth. You can think of these points in all of this ray. So I'm transferring just the point now to a ray, which all of them corresponding to the same projection by just a scale. Because this point will be AX, AY, and then A. Correct? Or let's say like A1, A1, A1. This one will be A2X, A2Y, and then A2, and so on and so forth. I can easily transfer from this point to the heterogeneous by just dividing by the scale and removing the 1. Correct? So now, just like geometrically, all of these points corresponding to the same ray. And I can easily go from one point to another point. This is just like to make sure that you understand this in the geometric domain, or what we are doing. We will go to that later on again, but here I found that it is useful to cover something like that. So let's see the transformation in the projection now domain. So now with the translation, we have this matrix. How about the scaling? We already showed the scaling in the 2 by 2, yes? But how it looks like in the new homogeneous domain. If you do the math, you will find that again, with this scaling, I have a scale in the x direction, I have a scale in the y direction, but I have 1 in the z direction. So this will be multiplied by that, this will be multiplied by that, and 1 multiplied by this, so I have done nothing. This is just like very similar to the 2D transformation. How about the rotation? The rotation is exactly the same. The cosine theta, if you remember in the diagonal of the 2D matrix, I have applied this, I have applied that, and I have added the 1, all of the others will be 0. And if you do the math, you will find that this is exactly the same things that you will get if you were to go with the 2D by removing the 1, or by transferring from the homogeneous to the heterogeneous domain. How about the shearing? The shearing is exactly the same. So 1 here multiplied by x and y, but then with this x dash, I will have a shear in the y direction. With this y dash, I will have a shear with the x direction. The others will be 0, and again 1 in my additional domain here, or my additional z direction, or my additional direction. Is that clear? Oh, so now, assuming that I have point x and y, and this in this domain, let's say like w, for instance. And then I have not only done one transformation, I have done multiple of these. So I took the point, for instance, rotate, and then shear, and then translate, and then scaled, and so on and so forth. So if you look at these matrices, the first one is just not but translation. The second one is rotation. The third one is scale. So all of this multiplied together with the x will give me the x dash, multiplied by the y will give me the y dash, with the w will give me the w dash, and so on and so forth. But does the multiplication order matter? Review the linear algebra, a multiplied by b multiplied by c. Is that equal to b multiplied by a multiplied by c, or c multiplied by a multiplied by b? Matrix multiplication will give you the same result. Yeah? So please review that. I don't think like the multiplication is reciprocal unless there is like a certain particular constraints. Or associative, what we can say here, associative. So now I would like to do a classification of my 2D transformation. So now I have a translation. I have my image here. This image can be translated as we already shown. We can do something called Euclidean. We'll understand what is Euclidean means for a second. And then we can also do similarity. We'll understand what a similarity also means. And then we can do an affine transformation or the projective geometry. Let's take one by one. But while we are doing all of these things, we would like to concentrate in an important stuff or an important parameter, which is the degree of freedom. And we'll understand why we need to do that in a moment. But this is something very, very important. We need to know what will be or what is the degree of freedom of each particular translation, each particular transformations, I'm sorry. So let's say if I have a translation, what will be the degree of freedom? If I have a rigid or Euclidean transformation, what is the degree of freedom, and so on and so forth. We'll cover this now. With this translation, how many degree of freedoms? So with this, if I would like to see like how many degree of freedoms, I will find that I have 2 degree of freedoms. Why? Because I can change T1 and I can change T2. T1 is not but the translation in the X direction, and T2 is not but the translation in the Y direction. So I have 2 degree of freedom. Okay. How about this? Assuming that I have what we call the Euclidean or rigid transformation, which is at rotation plus translation. So now with this, I have actually, my degree of freedom is 3. Why it is 3? Because I have 3 things to change. I have 2 in the translation. I have Tx and Ty, yes, this and this. And I have 1 in the rotation, which is theta. I just change the theta. If I change the theta, this is 1. If I change the translation in the X direction, this is another 1. If I change the translation in the Y direction, this is another 1. So now I have a 3 degree of freedom. I can change 3 variables. So this just shows you like why we have, what will happen to the image if this is increased, what will happen to the image if this increases, and so on and so forth. Now we are moving to another thing which is called similarity. Similarity is not but, as we have described previously, rotation in the rigid and rotation and the translation in the Euclidean transformation, but plus uniform scaling. So how many degrees of freedom I have now? So now with this, I have actually, my degree of freedom is 4, because now I have the scaling, I have my theta, I have the translation in the X and the translation in the Y. So I have 4 parameters to change. So my degree of freedom is basically 4. And this is in the similarity. How about the affine transformation? The affine transformation is scaling, shearing, rotation, translation. Shearing, by the way, I can call it also skewing. Yes, skewing. So by doing this, how many degrees of freedom that I have in this case? So now if you look at this, I can actually change 6 parameters. And because of that, the degree of freedom is 6. 2 in the translation, rotation is another 1, 3, 4 is the scaling, the shearing will be in this direction, the other direction, so I have now a total of 6. So this will be my affine transformation, which is not, by the way, you can just like multiply the matrix of the similarity, multiplied by the shear will give you the affine transformation, by the way. Okay, so now we just need to check what is each of these transformation preserved, for instance. So the properties of the affine transformation. Unfortunately, origin does not necessarily map to a certain particular origin, but my lines will map to a lines. Yes? The lines will not map to like a cylinder or circle or something else. The line will map to a line. Parallel lines map to parallel lines. If this is parallel, yes, when I transfer them, will be parallel. This is parallel, and transfer this and this will be still parallel. Ratio are preserved. So if I were to scale this to half, this also one will be scaled to half and so on. So the area will be, the ratio will be preserved between this and this to this and this. So the ratio will be preserved, but the certain particular area inside will not be preserved because there is an affine transformation. And then compositions of affine transformation will be also another affine transformation. How about the projective transformations? With the projective transformation, I have this, and unfortunately, this will be something like that, given this equation. How many degrees of freedom? The first thing that you will say that it is 9 degrees of freedom. But this is actually 8, and we'll prove later on why it is 8. But just like for now, you can change this value to 1. And if this is 1, I will have 8 degrees of freedoms. Because basically, if you change this to 1 multiplied by the W, it will give you like another value of W, but then you can divide by this W at the end. So this 9 can be transferred to 8. This is just logically. Yeah? But what's exactly preserved? The origin does not necessarily map to the origin. Lines map to lines. Parallel lines do not necessarily map to parallel lines. Ratio here are not preserved. Composition, projective transform are also a projective transformation. But now again, this is like the image plane. This is the point in the pixel coordinates and so on and so forth. What we would like to do next is the determination of a known transformation to that particular image.